So my name is Haya. I have a very difficult name, so if you butcher it, don't worry. Been through it many times. I'm a computational physicist at Los Alamos National Lab, and I will explain to you a little bit about what I do, but I don't have a whole lot of time to do it. But what I really want to do is, so my talk is possibilities, pitfalls, and practice of HPC research. So as a computational physicist, my primary role should be I do research on using computing as my skill set, my tools, and I do it in high performance computing, so at a very, very large scale. But I want you to think beyond that. We don't live in a box. When you get a real job, you are going to be asked to do things that your studies did not teach you to do. And so that is not a bad thing. It's actually where all the possibilities lie. So I wanted to explain to you how rich of an ecosystem the high-performance computing system environment is. It's not like, oh, well, you do support of HPC systems. It's not even like that at all, because the fact that you're working on one of the largest systems with one of the most cutting-edge processors put together in a way that no human could have or should have thought of, sometimes we think that way, it becomes this research environment where everyone has to work together to make it work. And because of that, there are opportunities. So if you do computer science, if you are working in an application, if you enjoy storage, if you enjoy coming up with workflows and helping, even like the web interface of how things all work together, there's so much research possibility in an HPC ecosystem. So I do scientific computing, the applications, and most people think that's where the research lies. Like, I think of a physics problem, and I put it on a computer, and something magically happens, and I write a paper. But that doesn't really, that's not really how it works, because standing up something that is very large, making it work correctly, you need your operations folks. System administrators are invaluable. I love my system administrators. I trust them with my life. I trust them with my correct results. So we often do papers together, because I rely on them. I rely on their expertise to understand such a delicate system. Data management is going to bite you all the time. You're not thinking about that because you're thinking, I'll just do my I/O at the end. Guess what? It can take up 90% of your time, or it can kill your application. So understanding data management. What are you going to do with your data? How long do you need to keep it? What if I want to do it at a different place than where I am physically? All of those questions are research topic as well. Programming environment and tools. If someone doesn't create the compiler, the tools, you have nothing. There's no sense of having a system where you can't run anything. So that also is a research environment, because you want to be injecting into how that gets developed. So you have to work closely together with people who are interested in the programming environment and tools. And like I said, HPC support and quality of service. Your system is going to go through software upgrades. So every time your computer goes through a software upgrade, you're like, damn it, there's a new bug. Like, what happened? And having that on an HPC system, it's the same thing, right? So you really need to have the infrastructure, the people who are smart enough to handle all of this and work together well. And so that's why I like high-performance computing, that kind of breaks down some of the hierarchy, because we all have to work together. All right, so what do I actually do? I'm a scientist. I try to solve problems. Like I said, computational scientist, computational physicist. I actually don't know what I do anymore, because at some point you just keep getting asked to solve a problem, and it doesn't quite fit in the box that you want to call yourself. So I'm just me at this point. I've worked at Los Alamos National Lab since 2015, so not a whole lot of time. I've been there for 2 years in the computational statistical sciences division. So you'll find, if you are interested in a lab, there's all these divisions, and shouldn't be that way. I think there should be more cross-talk, but you got to have a line management somewhere. So what do I do as a computational physicist? Okay, this is very complicated. Right now, I am the Trinity Center of Excellence Tri-Lab Team Lead. And what that means is I have a supercomputer called Trinity, and a Center of Excellence is to try and get applications thinking about the new hardware, getting ready for the new hardware that is Trinity. On the other hand, I was, or kind of still am, the Trinity Acceptance Lead, where I'm trying to get the new hardware ready for the application. So you buy a system and you think like, it's not like someone just delivers a system on your door and you open it up and say, oh wow, I'm going to turn it on. There's actually a long period of time where you have to get the system usable. So I did both directions in, for the Trinity project. My normal, what I do as scientist is low energy computational nuclear physics. So it's, what makes a carbon atom different from an oxygen atom? How exotic can oxygen be? Because you can keep throwing neutrons on there. When does it fall apart? If this reaction happens, what does a nucleus break into? So those questions are the things that I scientifically look at, and I do that through collaboration. So I'm a PI, co-PI for a SciDAC project, which means somebody gives us money and we work on questions of interest. I also have to write proposals for things like computing time. So Insight is writing up, we have millions of hours of computing time, but you have to compete for them as well. So you're competing for money, competing for computing time. ECP is exascale computing. So I also do, thinking about the next system. Other things I love to do are we run a parallel computing summer research internship at Los Alamos National Lab with a couple of cohorts in the room, so make sure you talk to them about it. We think we need to prepare the next generation because you might not be getting what you need at school. We want to give you the hands-on opportunity to experience it. That is the best way to learn. And I do a lot of professional community involvement, like Dorian was saying, cluster competition and the SC conference. I'm a paper reviewer for different conferences. I'm an editor for, they just ask you to do all sorts of stuff and I can't keep track of it. So my biggest concern right now in my life, other than my family and my well-being, is the Trinity supercomputer. So it was being birthed over the last year and a half at Los Alamos National Lab. A little bit longer than that. It's really annoying. So, can I move here? If I move away from it, it'll be better. Okay. So the Trinity supercomputer is big. And it's also exotic in the fact that it's not just like, your desktop. It has two different types of processors in it. So now you're like, okay, I created an application. How do I get it to run on two different types of processors? That's something that researchers struggle with, or we're going to be struggling with. But on the one side, the Intel Haswell is very conventional. It's what you see every day, what you're dealing with. It's what it's our warm and fuzzy type system because you put this scientific application on it and it just runs, and it feels good. But the other side is more forward-looking. It's the Intel Xeon Phi Knights Landing. And the potential for more performance, for more science to be gotten is there. But you have to exploit the hardware. You have to know how to actually write your code and put it onto the hardware correctly for you to actually get all of this, promise of performance. So it means that we're challenged as developers of, scientific applications by these new systems. Every new generation means we have to be a little bit smarter. We have to think more about how to actually use what we're given. Because if you don't, you're going to take a step back in your performance. You're leaving a lot of, there was no point in purchasing something that was, that had more capability. So it's like buying a race car but not knowing how to drive it, right? You want to learn how to drive it so you can use it to its full capability. So a lot of our code teams are thinking about how do we use this processor, to its fullest potential, and it's not easy. So that's why it's a research topic, and we work really closely with our vendor partners, Cray and Intel, to figure that out because this is almost the first time that they've seen this processor too, all put together at this scale. So it's this really great collaborative process of figuring out how to use it the best. There are other things about Trinity that are complicated, like it has this really giant file system. But on top of that, so I don't know if you've done any, file system work, but you want it to be faster all the time. You know, you want to be able to write out your data, read out your data faster, 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 because it's always taking too long, especially if you're doing a simulation where, you know, you're dumping out lots of data and then you need to read it back in. So there's something else, there's now new exciting things happening in storage where there's something called data warp, where it's this kind of interim layer of I/O where you can have it faster. It's a smaller amount of file system, you know, of storage, but it's much faster. So just every new layer that is added to the high performance computing system is a neat new research challenge, but it's also an opportunity for the applications to get more science out, to be more productive, if you're going to take the time to learn how to use it. So how did I get here? I mean, I don't think that there's any like graduate course that says like, oh, this is what you're going to do for your life, right? You just kind of morphs over time. So here's kind of how I got here. I'm just going to give you the highlights because there are a lot of gory detail. I started as a French major as an undergrad because I thought I'd do international business. I had no direction, and I don't know why my parents didn't give me direction. It was very bizarre. They forced my brother and sister to go towards the medical school path, and they said, hey, good luck. You're the youngest. Go have fun. So, but I took my first physics course as an undergrad, and I loved it. I got a B. I cried for probably 3 months, but I loved the challenge. I loved the not knowing. I loved something new every day. So I decided I was going to change my degree to physics. And I was able to have, you know, through 2 great mentors and 2 internships, I learned Fortran. Yeah, I love Fortran actually. And I was able to see what I don't want to do for my life, you know. So my first 2 internships showed me, I don't want to do these things. It's interesting, but I don't want to do it. So when I went into grad school, I decided, because I did internships in astrophysics, I'm going to do something a little bit more tangible for me, condensed matter physics. So I went into condensed matter physics, and then you'll see I took a summer hiatus for family reasons. You're going to make choices because you're not a student alone. You have a life, you know. So I took a summer hiatus, and it ended up lasting 5 years. I'm not going to give you the gory details of the 5 years, but at the end of it, I was a single mom with a toddler, thinking, what the heck did I do with my life? I thought I had way more, you know, in me. And I went back to grad school. Wasn't easy, but I did it. And I finished my PhD. I did it at San Diego State, Claremont Graduate University in computational science. And again, it was because of the help of great mentors, great advisors, that I was able to take my next leap and doors were able to open for me. I got into low energy nuclear physics. I've always loved quantum mechanics, so that was a natural fit for me. And then also, you know, their connection got me an opportunity to work as a grad researcher at Lawrence Livermore National Lab for 3 years. And then I highlight networking, networking, networking. It's from there that I was able to bridge out and, you know, made connections, found my next opportunities, went to conferences, volunteered. All of those connections are going to help you in your career. And I will show you why. I worked at Oak Ridge National Lab for about 8 years. Prior to joining Los Alamos National Lab. And again, I had a really great group leader help me to do a lot of great skill building so that I could get to the point where I can be the expert and do some of the crazy things I do today in my job. Okay. And so what are the challenges to high performance computing research? They're actually the same challenges that you will see in any career path. The pitfalls. You know, I think any career that you're going to go into, you are going to be asked to make a choice. You're going to be at a crossroads in your life where you have to make a choice. Grad schools or job or something. And you are going to make it with a lack of information, no matter what. You know, it's not like you can jump into the future. So, you know, the thing that you need to do is your due diligence. Make sure you ask the right questions. You go in there, you do internships, you understand work culture, you try and get as much information as you can. Don't be afraid to ask the question that you need to have answered in order to make a better informed decision about your life choices. Solicit feedback from people you trust. Create a mentor network. My sister is in my mentor network. She's my work-life balance coach because she's tired of me complaining about how much work I do. So she's like, you can't make a decision anymore until I approve it. So I said, okay. you're in my network now. And as well as, my professional network, I have mentors when I say, what do you think about this? I'm very fortunate to have my husband who's also in the field with me. We do kind of a little bit overlapping work, and I can ask him, what do you think about this? And so not every opportunity should be one you take, and it's great to have a network of people that can give you advice. Sometimes you have to leap and correct. I did that in my life. I have a missing 5 years, but you know what? You have to be able to say to yourself, I made a mistake, or that was great learning, and now I'm going to correct myself, and I'm going to try and do something that feels more aligned with what I want, what feels good to me, that feeds the soul. So don't be afraid to do that. That's probably one of the most important things. Don't stay in a path if you feel like it's not working for you. And then don't forget to put enough weight on life outside of work. When you're young, you're willing to sacrifice family and friends and everything because you're like, I'm so dedicated to my work. And then as you get older, you're like, what? You need to make sure you keep a balance and start thinking about things that are important to your life's well-being as well as you make your career choices. Even like really bizarre things like what food do I like to eat? I feel like I keep making choices that's contrary to that because I need Korean food, and every place I've been to in the last decade has no Korean food. So I have to go back to California often. The most important career decision you will make is who you decide to marry or who you decide to impact your career decisions. That is the most important. So make sure that there are people who are looking out for your best benefit. It's not always the case that we do that. So that's my pitfalls. And best practices. So all of my best practices center around making connections. Collaborate. This is a great room. You're going to make a connection with now 29 other people. Collaborate. Think about collaboration opportunities. See opportunity, see synergy. Think outside the box when you're like, oh, what do you do? Oh, I don't know what that is, so I'm just going to walk away. No, there's actually a good connection that's there. I've had the best papers with people that we do totally different things, and it's kind of neat to see that there's an overlap. Learn from others. Find someone who is successful and learn from them. Ask them, hey, can I read one of your proposals? That is the best way to learn, is from someone who has already done it. Talk to people, agree to things. At some point you're going to have to say no, but when you're young, agree to do things. Volunteer, review proposals, read other people's papers, be on committees. All of that is a learning opportunity to understand how the system works. Read the instructions carefully. I cannot tell you the number of proposals I've received where I'm like, did they even read the call? And it makes you frustrated as a reviewer. And write a lot, write proposals, write papers, and keep in mind, rejection is great. That is how you learn. You get feedback from your reviewers where they say, you should have done X, Y, and Z. They're not just going to say, this sucks. They're going to give you, feedback so that you can incorporate it into the next round. So write a lot. Publish to establish your credibility. That is why you're publishing. You're publishing to get your work out there, but you're also publishing because you are this entity that I'm going to Google on the internet at some point and say, oh, what did this person do? And that list, follows you around. Get a good proofreader if you're not great at writing. Make sure you have people who are available. Hey, can you read mine and proofread it for me? There's something called scientific reproducibility that's going to become big in your generation because in computing, it's been a little lax sometimes where it's like, I had some results and I've only done it on one supercomputer that no one can ever touch, ever, in one programming environment that no one has. We want to be able to reproduce scientific results just like you would in a lab. You don't want, this cancer drug to be written, to be created off of one result. So you need reproducibility. And build and share your expertise, and people will start to come to you and ask you for a lot of stuff. So my last parting result, Daniel said I have like 30 seconds, is that I'm going to leave you with something one of my mentors said to me when I was at Oak Ridge. She said, you're smart, you can figure it out. So the way that this story works is when I was in 4th grade, my teacher kept giving me a C on all of my handwriting assignments. And if you're the child of an immigrant, that is not acceptable. And I was mortified. So I didn't know what to do. I said, teacher, what can I do? And she's like, well, you're just a C handwriting student. I'm like, what do I do? I entered into a district handwriting contest where it was anonymous. Nobody knew who you were, and I became a finalist. And guess what? My grade was an A from now on. So that external validation, right, to overcome whatever bias she had against me was really important. And that worked for me at work too. I had a very difficult time with a couple of managers at work. They had some sort of beef against me. I couldn't get past them. I was frustrated, and I told my mentor, Reka, what should I do? I'm going crazy. And she said, you're smart. You can figure this out. And she outlined for me what that meant. She said, instead of thinking this way and being frustrated, build this way. You are more than you. You can build locally, nationally, internationally, your reputation. This is a positive direction to head into, positive place to put your energy, and then now you are way bigger than the problem that was there, and it will help you overcome it. So that's the advice I'll leave you with, and Damien will have to attack. So I apologize. I have to run, but I will be